Welcome back to Elements of Chemistry. In this chapter, we're going to talk about the history of the atom, and we're just going to give you a brief timeline of the important events. So, when we start talking about the history of atom and the atomic theory, we have to start with the ancient Greeks. Back in 400, BCE, Lysippus and Democritus, they were philosophers, not scientists. So, philosophers, they sit around and talk and use the argument of language, not science. So Democritus was a student of Lysippus, and he wrote about matter being discrete particles, and he first coined the term the atom. He envisioned the atom to be a small, solid sphere. Now, Lysippus and Democritus weren't the most popular guys at the time. Aristotle and Plato were the big players. They were the original influencers. And they had a greater influence. So Aristotle's theory is what people believed. Even though Democritus was closer to what was right, people believed Aristotle. And since he was really the original influencer, they believed him, even though it was wrong. Aristotle believed that all matter was composed of four elements: earth, air, fire, and water. A bird could fly because it was made of earth and air. A rock was hard because it was made of earth. Um, cheese was made of a combination of earth, water, and fire because it came from a warm animal. You were a combination of the three: earth because you went back to earth, air because you had air in your lungs, and when they drowned you, air came out, fire because you were warm, and when you died, you lost the water and went back to earth. So everything could be argued being made of those four components. Well, nobody wanted to go against Aristotle. So that theory held for a very long time. Between 400 BCE and basically 1800 AC, we had the age of the alchemists. The alchemists discovered a lot of lab techniques. The alchemists are credited with the discovery of strong acid bases, distillation techniques, advances in glass making, advances in metallurgy, being able to separate mixtures, figuring out what was pure and what was a mixture. They had advances in dye making, inks, accredited for gunpowder. They had the early attempts to organize and categorize the known substances, which some were starting to use the term elements. They started identifying elements as being pure substances. But nobody was brave enough to go and say, hey, Aristotle was wrong. So in 1808, John Dalton came along, and he was a school teacher, not a scientist. So far, the alchemists are the only ones you could call a scientist. And really, they're credited with trying to find the elixir of life, postponing death, and turning lead into gold, base metals into gold. And they found a lot of other things on the way to not getting those accomplished. But John Dalton, a school teacher, he was the first one to really openly take a stand against this Aristotelian theory. Okay, Dalton had his five postulates. The first postulate: elements are composed of tiny particles called atoms. Good, he brought Democritus back. He said that all atoms of a given element show the same chemical properties, and atoms of different elements have different properties. He said the atoms are not changed in a chemical reaction. He said all atoms of an element were identical to all the other atoms of that element. Well, that wasn't quite true. He didn't know about isotopes. He didn't know about subatomic particles. Realize this is 1800. Okay. He said that atoms can't be subdivided, created, or destroyed. This had to be changed later once we discovered protons and neutrons. He said compounds are formed when atoms combine in simple whole number ratios. This led to the law of conservation of mass, the law of multiple proportions. The masses of one element, when combined with the fixed mass of a second element, are in a ratio of small whole numbers. Okay, what does all that mean? It means you can't have half an atom. Everything is made of single whole atoms. You can't have pieces of an atom. Because remember, they're indivisible. So water, we now know, is made of one oxygen and two hydrogens, not one oxygen and one and a half hydrogens. Okay. So you have to have a whole number of atoms. He also said that chemical reactions, atoms are combined, separated, or rearranged, but never created or destroyed in the process, that all atoms have to be accounted for, essentially the law of conservation of mass. So Dalton and his postulates brought back Democritus's theory. But still, we have the atom as a small solid sphere. Okay, just put in as an aside, it wasn't until 1869 Mendeleev first published his periodic table of elements. So we're graining elements, but this solid sphere model holds for quite a while. In 1895, William Röntgen, and there really should be two dots over that O for the Röntgen, he discovered cathode rays. He was playing with fluorescence. He realized some minerals emitted high energy rays. If you put a rock in the sunlight, it could gain energy and it would then glow in the dark. And one day he had a rock that he didn't expose to sunlight, put it on some photographic film that was in a drawer, wasn't exposed to sunlight, didn't take the picture, decided, did I use this or not? Developed the film plate and discovered an image. And so down the road, he's famous for taking the very first X-ray image. He discovered X-rays. Didn't know what they were, so he called them X. And the very first X-ray was actually of his wife's hand, and you can see it there with his picture, and you can see her ring on her finger. Okay. Shortly after, J.J. Thomson comes along, working in Great Britain. He's playing with cathode rays. Electricity was new. You had a positive and negative plate, and you could develop a stream of particles going from the cathode to the anode. Well, he took this stream of particles and passed it through a magnetic field and realized that it could be deflected. Since the atom was neutral, these negative particles had to be balanced by some positive charge. And this gave rise to the first real atomic model. We call it a plum pudding model. So if we look at his model here, we have negative charges embedded in a positive matrix. If he was an American, we would have called it the chocolate chip cookie model because it looks like chocolate chips embedded in the cookie. He was a Brit. All their desserts were called puddings. And basically, he was saying this was raisin cake. It's raisins embedded in a matrix. But the plum pudding stuck. Okay. 1900, Becquerel and the Curies were doing some work. The Curies were students of Becquerel's. They were also studying fluorescent materials, and they noticed that different particles could be deflected different ways. The real lab master here was Marie. Pierre was great at getting funding, doing the management, doing the writing, but Marie did all the hard work. She literally ground down a room full of rock to get a very, very small sample of their first radioactive elements, which was named curium for her. But she was the one who suggested the name radioactivity and coined the terms for the particles alpha, beta, and gamma. Those will become important when we get to our nuclear chapter. Okay. Following Thomson's work, Robert Millikan in 1909, doing his famous oil drop experiment, determined the charge to mass ratio of the electron. Okay, what he did was he took very fine oil drops that were basically spread through an atomizer, like a old-fashioned perfume bottle that you squeezed the end and it made little tiny droplets. He passed these through a metal plate so that they came through as a single droplet. This plate was charged, and by adjusting the charge on the plate, positive, negative, he could get that dot to float in space. And by doing this, he could figure out the exact charge and the exact mass of an electron. Okay, moving on to Rutherford. Rutherford's a New Zealander, but he was working at the University of Manchester. Rutherford was one of those professors that had a huge group of laboratory students. His more famous were Geiger and Marsden, or like Geiger counter fame. Okay, so Rutherford's working with this radioactivity from the Curie's work. So they're following up. There's a lineage here. Rutherford and students took a radioactive sample and they put it in a lead block so that it could only come out one direction. They passed that beam through charged plates and they determined that alpha, beta, and gamma deflected differently. He figured out that the alpha had to be positive because it was attracted to that negative plate. Beta was negative because it was attracted to the positive plate. And he could show that the alpha was heavier than the beta because it didn't move as much. It had more inertia. It took more energy to get that particle to bend. Okay, he then took that alpha ray and used it in his famous gold foil experiment. Still using that lead block, but now they're isolating it so that they're just shooting alphas, okay, at a very thin sheet of gold foil. That gold foil was only a few atoms thick. As expected, those alpha bullets, we're going to call them, went straight through or were deflected slightly. But some of those bullets actually bounced back. Those positively charged alpha particles ricocheted. That meant that they had to have hit something hard and dense and positively charged. So he realized that the atom wasn't an even matrix of positive and negative charges, Thomson's plum pudding model. Because if it was Thomson's model, all of them would basically go straight through. He said that there had to be some dense, solid core to the atom, which he called the nucleus. And he surmised that the nucleus had to be positively charged because the particles ricocheted back. Likes repel likes. So those positive charges had to ricochet off another positive charge. So Rutherford's credited with the nucleus is positive, and he believed that that positive particle existed, and he called it the proton. He also knew that the mass of the atom was such that there had to be something else in there. So he predicted the presence of the neutron. Okay. Niels Bohr, working in a total different field of science, Niels Bohr, fabulous mathematician, he was studying spectral lines of light. If you heated up or shined light of certain energy on different metals, light could be given off. This is like the light bulb. Why were we getting that? And it was giving us in different colors. And he realized that when atoms, when they're excited, light could be emitted, and that was the electrons jumping up as they absorbed energy to a higher orbital position. And when the electrons fell back to their ground state, their home spot, they would release that same amount of energy. Okay. So Bohr put the electrons into orbit in discrete quantized energy levels, representing those colors of light. Not all the colors were visible. Some were in the infrared, some were in the ultraviolet. Okay, so he was the one who said that the first orbit around the nucleus had 2 electrons. The second hold 8, then 8, then 18, 18, 32, 32. He introduced what we call the planetary model, where the nucleus is like the sun and the electrons orbit around that. Now, these 2, 8, 8, 18, they match something really unique. Mendeleev's and this periodic table had some revisions over time. We had a change to account for atomic number. Remember, each square as you go across, we're adding a proton. Well, if you notice carefully, this first row in the periodic table, there's 2 elements because the first orbit holds 2 electrons. The second row holds 8 elements because the second orbit holds 8 electrons. The third row, 8. So do you really have to remember 2, 8, 8, 18, 18, 32, 32? No, you just look at the rows on the periodic table. And remember those bottom 2, the rare earth metals, those fit into that gap on the periodic table. So there's starting to be some patterning to not only how the elements react, how the periodic table is set up, but to how those electrons function. Okay, come along 1926. This is called the Schrodinger quantum model. Some people call it the Schrodinger-Heisenberg model. Some just call it the quantum model. In the quantum model, Schrodinger was building on the work of Louis-Victor de Broglie. And de Broglie's credit is he said that everything had a particle wave duality. If it has mass, it has a particle nature and a wave nature. And he showed mathematically that electrons travel in what we call probability clouds around the nucleus, around the atom. And the distance and the shape of these clouds are determined by the wavelength and governed by a set of quantum rules that we will get to in our nuclear chapter and our electron chapter. They had places where they were most likely to be found. So if we look at this and summarize it, Democritus said that there was a shape or quality to the atom. It was a chunk of something. Dalton said they were different sizes, densities, but a solid sphere. Thomson had his pudding model, where you had positive and negative charges embedded like chocolate chips in a cookie. Rutherford had the nuclear model, where you had a solid center that was positively charged and the electrons distributed in a region of space around it. Bohr put the electrons into energy levels, and then Schrodinger put them in probability clouds. A couple of other places you might want to look. Crash Course Chemistry has a fabulous video going through the history of the atomic model. I really do suggest you watch that. But for our quick flyby of atomic theory, there you go. As always, stay curious, be safe, have a wonderful day, and a good tomorrow.